Hi everyone, Mr. Lee here. In this video, we're going to go over methods of charging and the law of conservation of charge. Now just keep in mind, right now we're just doing the basic ideas, a couple of sketched models, but the important thing is that in class we'll be practicing these methods of charges throughout the days. So let's begin. So the first thing that we should go over is the conservation of charge. So what the conservation of charge is that the amount of charge you have in the beginning must equal to the amount of charge that you have at the end. Okay, so I wrote it in formula form, but it's a very easy concept to really think about, right? If you start off with positive 5 coulombs in the beginning, then you must have positive 5 coulombs at the end, right? And so this idea here is this idea of a closed system, meaning that no amount of charge enters or leaves and everything remains the equal amount, okay? Now, this idea is a very powerful idea because we can apply the idea of the system to any scenario. So a system could be as small as, let's say we have a positive, negative, positive, and positive, right? So if this is our system, and just so you know, when I draw the system, I like to use the dotted line here to indicate that that's the system. This system is a positive 2 charge, right? So what this tells us is that no matter what happens at the end, we must always have a positive 2 amount of charge. Okay, now, so this is a very specific example. Now, let's say we zoom out, right? We zoom out all the way back so that we're looking at, I don't know, let's say the entire universe, right? So if we're taking a look at the entire universe, and this is like pretty out there, this is pretty bizarre, but what this tells us is that the amount of charge that the universe started off with will be the same amount of charge that the universe ends with, right? Charge cannot be created or destroyed, much like mass. All right, now the other thing is the idea of a closed system. So the closed system and the open system just means that the system either gained or lost charge, all right? And this doesn't go against the conservation of charge, but it's just like a kind of like a little addendum to it. So for example, let's say here we have our system, right? So same idea here, we have positive, negative, and positive, positive. So here we have a positive 2q. So let's say we removed a negative charge. We remove this out. We shoink it out. So because we are altering the charge initial of 2q, right? So we shrink it out, and now we have a system that looks like this. Plus, 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 and now we have this negative over here. So if we're looking at this system here, we now have a positive 3q. But if we just extend the system out even more, so that we include the one thing that we shrinked out, now we have a negative 1q. So our total amount of charge is still plus 2q, but our scope, our vision, is just the system that we chose. So therefore, we can say this is now an open system because we can alter the amount of charges of our focus. Okay? All right. So now let's go into the methods of charging. The first method of charging is what we call polarization. So let me get there. Polarization. So with the idea of polarization, the big thing here is that there is no physical contact made. Okay, physical contact. Now, this is just a generic way of thinking about it. Like there could be contact that's involved, the polarization. Let's just say there's no contact that is made. So the idea of a object is that for every positive charge, you have a negative charge, right? For every negative charge, you have a positive charge. And because this system here is what we consider to be neutral, right? We just view it as just a point mass or a point amount of system. And so the idea of polarization is, let's say we have this object, right? Let's say we have this ball. Most commonly used in class, we'll use a balloon, all right? So if we were to bring a charged object, let's say we have a large positive source right here, and we bring it close. Remember Coulomb's law, we have the inverse square relationship. So the closer we bring the object, the more force exists. So we have this really positive source, and here we have this object that has, or this system that has both positive and negative charges. So what ends up happening is that all of the negative charges will gather as close to that positive charge as possible, leaving the remainder to be just the positive charges. Now, here is a very important idea, so I'm going to type this out here. Whenever we're talking about charges and how charges move, we have to always assume the following, okay? Only negative charges can move. All right, so the way that I drew it here is I made sure that the negative charges are the ones that are being brought close to that positive charge. Now, just to really showcase this idea, we'll go into the reasons why only negative charges can move. But let's say instead of a positive source there, we have a large negative source and we bring it really close, okay? And so remember, the positive charges don't move, instead the negative charges move. And so because like charges repel versus here, this is unlike charges, they attract, right? Like charges repel, all of the negative charges will be as far away from the object as possible, leaving the closest side to be positive. Now keep in mind, only the negative charges move, the positive charges were always there. It's just the negative was like, let's get away, right? As far away as possible. Now, the reason why we say that only negative charges move is that within an atom, right, the nucleus has the neutron, and it has the proton. And because the protons carry the positive elementary charge, and the nucleus actually physically makes up the object itself, right? We are not saying that the physical object doesn't shift, okay? Because I mean that would be weird, right? So imagine here in this scenario, if this was actually like a ball, right? What this would show you is that the ball would like kind of like shift to the left because the positive charges moved, and that doesn't happen. Okay, the positive charges, they are stationary, they are bound within the nucleus, right? They do not move. This is very important. This is so important. It's one of those, put a little star next to that idea, okay? So you can really see those in the MCQs. So only the negative charges move. Now, the amount that they can move, this comes into the idea of two different kinds of material. The first kind of material is what we call a conductor, and the second kind of material is what we call a insulator. So for the conductor, what we can say is that the negative charges move freely, and I'll show you an example of what that means. In the insulator, we say the negative charges are bound, right? So they do not move freely. So the a conductor, the most common conductors that we use are is like pieces of metal. So let's say we had a like a metal rod here. Okay, so we have a metal rod here, and we bring a, let's say, a large positive source close by. And so because this metal rod is a conductor, what this means is that normally the atoms have a positive and a negative charge bound to it, right? Just like this. But within a conductor, the electrons can move freely. So even though we have, let's say, it looks kind of something like this, if we were to zoom in on this metal rod, right, it would look something like this. So what happens is that if you bring a large positive source here, all of these negative charges that I drew, here, what they would do is they would just whoop, zoom as close to the edge or as close to that positive source as possible, leaving the remainder of the conductor to be positive. Remember, those positive charges did not move, okay? So polarization makes a object like polarized, right? One side is positive, which is the left side here, and it makes one side a definitive negative. So with that, that's like an example of a conductor. An example of an insulator is like plastic, right? Plastic is a insulator. So the same idea up here, right? Much like up here where we said every atom has a positive and a negative, right, associated with it, whereas a conductor, all the negatives can move, right, as far away as possible. What the insulator does, it says, no, you're not going to go anywhere. You're going to be as close to me as possible, right? But the negative charges, right, if we're looking at this positive source here, but the negative charge is like, I want to go over there. I want to go all the way to the right, right? But the positive charge is like, no, you're staying here with me. And so instead of a stark polarization that looks like this, what ends up happening is that the area that's closer to the positive charge, so let's just say this chunk of the insulator, right? Watch what happens here. This chunk of the insulator, we have the negative charges kind of like skewed to the right a little bit compared to, watch what I do here, right? Positive and negative, positive and negative, positive and negative, positive and negative. So these negative charges are still with their positive counterparts. But as I draw this, look what I do. Okay, I'm going to make the negatives a little bit closer to the right. Okay, a little bit bound, but a little bit closer. And then the closer we get to the positive charge, we can make it less bound. So here we see that the negative charges are bound to the positive charges, but here we can see that the negative charges, they're still bound, but they're kind of like stretched out. So the idea here is that the polarization over here, the net, if we're looking at this here, right, this area looks more or less negative because we polarize it compared to here, which looks more or less neutral. All right, which is very different from the conductor where the left-hand side looked positive versus the insulator that looks neutral. But the side closer to the positive charge, it definitely looks a little bit more net charged. All right, yeah. So with the idea of conductors and insulators, let's go over the method of charging. They call it like charging due to friction, but the scientific term is called the triboelectric method. Triboelectric method. So this is the friction method. the most common example that we use is, let's say you're on carpet and you rub your feet against the carpet and you touch like a metal object. So if you ever happen to have had this to you, you would feel a little shock that occurs. Now, another common example is if you're driving, right, when you go up to the gas station to pump your gas, right, as you leave your car, right, your butt and your back rubs against the car itself. And so when that happens, that rubbing or that friction action, it charges you, so that when you touch the gas pump, there's a tiny little shock that occurs. Okay. Now, the way that you charge objects due to friction is just that, right? You just get two objects and you just rub against each other. And so when that happens is that some objects will lose a negative charge, some objects will gain negative charge. Now, remember here, only the negative charges move. Okay, so let's say we have two objects. In class, we'll use animal fur. So we have a insulator. Okay, this is we might use plastic, we might use PVC, and then we have this fur. Okay, so when we rub the fur on the insulator, what happens is that the areas that your fur is in contact with the insulator, okay, as we rub it back and forth, some of the negative charges here, it'll jump onto the PVC pipe, or some of the negative charge on the insulator will jump onto the fur. Okay, and the way that we know how the objects are charged is what we call electron affinity. Okay, so what this means is that some objects are more likely to give up their electrons or receive electrons. It really depends on the materials that you're using. Okay, so when you rub the fur on the insulator, some electrons will jump off onto the other object. Now keep in mind, it's only the areas of contact. Okay, the rest of the insulator, because you didn't touch it, right, there is no distribution of charge. Okay, so that's the triboelectric. Now keep in mind, if we're looking at the system as a whole, okay, back to the conservation of charge, you still have the same amount of charges. It's just that some charges left the rabbit fur onto the insulator or vice versa. All right, now the other important thing here is that with the triboelectric, there is contact that is made. Right? There is physical contact. All right, the next is what we call conduction. Okay, so the idea of conduction, and we'll do two different examples of this. The idea of conduction is that you have one charged object and you have one not charged, or like a focal object, right? One other object. Okay, so here we have a scenario like this. So let's say we have a object that is negative, let's say -4 charge, okay, and let's say we have a neutral object, right, or 0e. So the idea of conduction is when this charged object, it touches, so there is contact that's being made, right? What happens is that because the system overall wants to be as neutral as possible, okay, the charges will distribute themselves so that both objects approach neutrality. So even though this object is neutral, because this one is far away from being neutral, okay, within the system here, what happens is after contact is being made, this will become -2e, and this one will become -2e upon touching, right? And so the conservation of charge still applies. The total net charge of the system is still -4 in the initial and in the final, right, as neutral as possible, so almost a even split. All right, now the difference is between insulators and conductors. Okay, so the important thing is that for insulators, when the method of conduction, or the method of charging of conduction occurs, only the location of contact is charged. Okay, much like the triboelectric for insulators, okay, versus a conductor. And in the example before up here, right, that was more of a conductor example. Charges are distributed throughout. Okay, so let's go into a example of this. So let's say, I'm going to try my best for the insulator to sketch it out this way, but let's say we have a -2e here, and here we have let's just say it's a 0, right? When this negative object touches this neutral object, and we'll just make it negative, it looks like this, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4. Okay, so net -2 here. So let's say we have this portion of the object touch this portion of the object. Okay, so with insulators, only the contact points from right there and right there become as neutral as possible. Okay, so this is one of those conceptual things. most of our examples will be thought of as conductors. Okay, so let's go into a conductor example, which is a little bit more clear cut. So with the conductor example, right, same idea. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. Okay, so we have this negative 2e, and it touches this neutral object. So one thing that I want to point out is as I draw this negatively charged object, see what I do here, right? I made sure that I drew my negative charges closer to the outside perimeter, and that's because like charges repel, right? And in conductors, we can say that the negative charges flow freely. So what this means is that for an insulator, this negative charge is probably right hovering above that positive charge. But because we're in a conductor, right, the furthest point that this negative charge is from this negative charge is on the outside perimeter. So if I were to exaggerate this drawing, it would look something like this. Right, so this is my negative charge on the outside, leaving the inside more positively charged. Okay, so when you draw it, just make it a point to draw the negative charges closer to the outside perimeter, especially when we're talking about conductors. Okay, so when this conductor touches this neutral object, okay, it'll be a even split. So we have negative 2 here. So this is 0. So what will happen is one negative charge will hop off here. Okay, and it'll go to one of the outside edges. So at the end of it all, this object here will be a negative 1e because it lost an electron, and this one will become negative 1e because it gained an electron. And just so you know, make sure you draw those electrons on the outside edges. Okay, so we have conductors, we have conductors, we have insulators, we have conduction, we have friction, and we have polarization. And the last thing that we're going to look at is called grounding. All right, so the idea of grounding. The Earth itself, or any large object, so let's type this out. So we can say any large object is a source of, I'm going to put this in quotes, infinite charge, or a infinite source. Right, infinite, a source of charge. So what this means is that we can assume that the Earth or any large object to be as neutral as possible. So when we have let's say we have a charged object or a charged sock, right? So we have negative 9e. We have this charged sock as negative 9e, and then we have u. So if I were to draw a stick figure, if you were to touch this charged object, because you are a large object, and not only that, but you are actually touching the Earth itself, okay, what will happen is this Earth is a infinitely grounded or a infinitely neutral sink. So what happens is that all of these negative 9 charges, right, it's like, whoa, I want to be as neutral as possible, and this ground here is like, whew, let's make this ground as neutral as possible, right, because everything wants to be as neutral as possible. So all of these negative charges that's on your charged sock will be like, let's get out of here, right, and it'll go into you, and it might even go into the Earth. And so when this happens, what you experience is a shock, where there is a leap of charge, okay, and you feel it, and you definitely see it, and we'll be playing with the Van de Graaff generator in class as we talk about this idea here. Okay, so after all this happens, we can say, even though the conservation of charge says, well, what happened to those negative 9 negative charges? Well, they're in the ground, and the ground is so big, it's like it made a tiny, minuscule dent in the total net charge, and it's still basically neutral, right? And so after the negative 9 charges left the object, we can now say that the object, oh, there goes my hand, the object itself is essentially a neutral object now, because we grounded the object. Yay. All right, that's that. I'll see you next time. Bye-bye.